Okay, we're going to have a think now about Newton's laws of motion. So Newton, in an act of incredible genius, reduced motion down to 3 simple laws. The first of those laws tells us what happens to an object if there are no resultant forces acting on it. And what Newton said in the first law was that if an object has no resultant force on it, it will either be at rest or it will move with constant velocity in a straight line. So the first law says that an object will remain at rest or move with constant velocity unless a resultant force acts on it. That might seem kind of obvious to us, but it was not obvious to people before Newton. Prior to Newton, the main accepted theory of motion had been due to someone called Aristotle. And Aristotle had taught that objects need a force to keep them moving, which in a way seems to make sense. If you have something with your car or something and the engine stops, the car will probably come to a halt. But of course what we now understand is that the reason for that is because the car is slowed down by frictional forces. If we could take friction away, for example, if we had a spaceship in space where the engine suddenly stops, what would happen there? Well, what Newton would say is that that object, if there are no forces to change its motion, it will keep the motion it's got. So if our spaceship was already moving and the engine suddenly failed, it will just keep going in a straight line forever and ever. There's nothing to stop it, there's nothing to speed it up. If we ignore any passing asteroids or any collisions or any gravitational effects, if there are no external forces on it, that object will just keep going in a straight line forever and ever. Sometimes called the principle of inertia. As I say, it seems in a way obvious, but it wasn't obvious prior to Newton. What that means, of course, in Newton's theory of motion, is that the effect of a force isn't to cause motion so much as to cause a change in your motion. So when we put a force on an object, it will either speed it up or slow it down, or maybe it'll cause it to change direction. And the second of Newton's 3 laws tells us how a force affects the motion of an object. What Newton said is that when you put a force on an object, the force causes an acceleration. Now, if you put the same force on a light object, you'll get much more acceleration. If I give a push to a table tennis ball compared to trying to push something quite heavy like a car, then I'm going to get much more acceleration when I push the light object. So Newton realised that the effect of the force depends on the mass of the object as well. So the equation which he came up with, which we now put quite simply, this was force is mass multiplied by acceleration. Okay, if you like triangles, we could have one here. Force is equal to mass times acceleration. And what that means is that the force is equal to the mass times the acceleration. The mass is equal to the force divided by the acceleration. The acceleration is the force divided by the mass. In fact, that is almost a definition of what force is. A force is what you need to make a mass accelerate. 1 Newton of force gives 1 kilogram, an acceleration of 1 metre per second squared. Force is mass times acceleration. The only other thing you need to know about this, by the way, is that the force here is what we call the resultant force. So if you've got more than one force on your object, you add them up. If I'm pushing the car forwards and someone else joins me, we add up our 2 forces and that gives us the resultant force. Or if I'm pushing forward and someone else is pushing backwards, we take my forwards force and subtract the backwards force. That gives us the resultant force. We'll see that that's important when we look at things like terminal velocity. So number one, law said that the principle of inertia says that an object remains at rest or continues in uniform motion, constant velocity in a straight line, unless it's acted on by a resultant force. Take away the forces, or where the forces are balanced, then you'll have uniform motion or no motion at all. If the forces aren't balanced, if you have got a resultant force, then you get acceleration. And the second law tells us how the acceleration and the force are linked, and they're linked by this equation: force is equal to mass times acceleration. More force on the same mass gives you more acceleration. All of those laws, both those laws so far, really just applied to a single object thought of on its own. The third law is different. The third law tells us that forces come in pairs, and that for every force there is an equal and opposite countering force, there is an equal and opposite reaction. So the law is sometimes put this in these terms: for every action there is an equal and opposite reaction. Or putting that in other words, forces come in pairs. If I put a certain force on the wall, suppose I'm pushing on the wall is pushing back on me. That's why my hand doesn't just go straight through it. I put a force on the wall puts a force back on me. A slightly odder example of this is a car. When a car is driving forwards, the tyres are spinning round, they're actually putting a backwards force on the ground, and the ground is putting an equal and opposite forwards force on the car. Every action has an equal and opposite reaction. So in a strange way, it's actually the ground which is making the car move forwards. That's not as surprising as it might seem, because imagine if you were trying to walk forwards on ice, on pure ice, which was completely smooth and where there was no friction. Every time you move your foot backwards, there wouldn't be a frictional force, so you just slide backwards and it would be impossible to walk forwards. So, third law: for every action there is an equal and opposite reaction.